Have you ever wondered why even the tallest trees don't reach the dizzying heights of our modern skyscrapers? It's a fascinating question that boils down to the limits of biology. Trees are the giants of the natural world, but they face fundamental physical and biological constraints that limit their maximum height. Let's explore these challenges. While the tallest skyscraper can soar over 800 meters, the tallest known trees, like the coast redwoods, max out around 130 meters. What sets this natural ceiling? The limits on tree height are primarily categorized into three main factors: the difficulty of water transport, maintaining structural integrity, and the energy cost of growing and sustaining such massive structures. First, the biggest hurdle: water. Imagine trying to pump water up a hose that's over 100 meters high. Trees face the relentless force of gravity in their quest to deliver water to the highest leaves. Trees use specialized tubes called xylem to transport water from the roots to the leaves. This is a passive process, relying mostly on natural forces rather than a mechanical pump. This transport works through the cohesion tension theory, where water molecules stick to each other, and the evaporation from the leaves creates a tension, essentially pulling the column of water up. However, as the tree grows taller, gravity exerts more pull, and friction within the narrow xylem tubes increases. This drastically limits how high water can be pulled before the tension breaks the water column. The second major limit is structure. The taller a tree gets, the more vulnerable it becomes to natural elements, especially wind and its own massive weight. To support extreme height, the trunk must grow disproportionately thicker at the base to maintain stability. This requires massive amounts of wood and energy just to resist bending and breaking. High in the air, trees are exposed to wind shear, which dramatically increases the risk of the trunk or branches snapping, making it a severe evolutionary trade-off to grow taller than your neighbors. The final major constraint is energy production. Trees grow to maximize the amount of sunlight they can capture, but growing too tall actually starts to reduce their net energy gains. The stomata, tiny pores in the leaves, need to open to take in carbon dioxide for photosynthesis, but they also lose water this way. At extreme heights, leaves experience more water stress and close their stomata more often, leading to reduced energy production. The energy needed to simply maintain the vast amount of non-photosynthetic tissue, the trunk and branches, increases exponentially with height, eventually outweighing the energy gained from the highest leaves. So, trees don't grow as tall as skyscrapers, not because of a lack of ambition, but because of the fundamental laws of physics and biology that govern water, structure, and energy. The maximum height of a tree represents a biological sweet spot, a trade-off where the benefits of accessing more light are precisely balanced against the compounding costs of gravity, wind, and maintenance. While human engineering overcomes these limits with pumps and steel, nature's giants are capped by their own internal plumbing and structural material, leaving the coast redwoods at the ultimate frontier of botanical height.